Hello and welcome back. If you are new here, please subscribe to the channel and activate notification bell button to get notified when we upload new videos. Thank you. Today we will create a fun little project, using LDR, which stands for Light Dependent Resistor, and NPN 29N3904 transistor. Our goal is, by using these two components, to power the load, depending whether there is a light or not. Or simply put, when there is a light, our circuit is off, and when there is no light, our circuit is on. So, let's get on with the video. First order of business is to learn what is LDR. It stands for Light Dependent Resistor. It is type of resistor whose resistance changes in the presence or absence of light. Simply put, when light goes up, resistance goes down, and when light goes down, resistance goes up. Simple enough. If you think that this is something extraordinary, just remember that this entire series of videos is dedicated to transistors, who are, in a nutshell, base current dependent resistors themselves. When base current goes down, collector current goes down, and vice versa. Who would have thought? Also, there are two ways to represent LDR component in the electrical circuits. Type 1, on the left-hand side is with the rectangle inscribed in the circle. On the right-hand side is Type 2, with saw-shaped line, inscribed in the circle. Similar, as how resistors are represented in electrical circuits as well. Two arrows pointing towards circle, represent light being shined on the LDR component. In our videos, we will use Type 1 symbol, one with rectangle inscribed in the circle. Now, with definitions out of the way, let's see what logic we can implement in design of this light-controlled switch circuit. What first comes to mind, is to use LDR as base current regulating resistor. Let's assemble a simple circuit containing LDR GL5506 resistor, NPN 29N3904 transistor, and 3 volts power source. Logic would suggest that, when light goes up, resistance of LDR goes down, there is a base current, our transistor is properly biased for saturation mode, and the circuit is powered up, so load is on. Vice versa, when there is no light, resistance of LDR goes up, there should not be any base current, our transistor is in cutoff mode, and the circuit is powered down, so load is off. So, what is wrong with this circuit, and why the warning? If you try to implement this circuit in real life, your transistor will burn out, and more likely than not, your power source as well. Here is the problem. We do not know what range of resistance the LDR has, when the light is on or off. Let's find out. We can download and consult the datasheet for this particular LDR and find out what is the resistance range. So, let's do that. Here is the info we need. This is excerpt from datasheet with information regarding resistance parameters for our LDR GL5506 resistor. Let's take a closer look. Okay, so let's start with first column from the left. These are all various types of LDRs. These are all generic components, manufactured from myriads of manufacturers. They all have the same specifications. For purposes of this video, we are only interested in the first row parameters. So, the mark for our LDR is 5506. Next column is light resistance in kiloohms, when light has intensity of 10 lux. That is a very dim level of light, roughly equivalent to the illumination from a single candle 1 meter away, or the light level just after sunset. So not very bright, but there is still some light present. We can still see pretty good in that light. In these light conditions, the typical resistance of LDR is between 2 and 5 kiloohms. Okay, next column tells us the resistance of LDR in dark. So, when there is no light present, the typical resistance of LDR is 0.1 megaohm, or 100 kiloohms. In this case, the dark doesn't mean absolute dark, just that, there is no active light source near the LDR. Gamma is used for calculating logarithm of the ratio of the standard resistance value under 10 lux and that under 100 lux. Not very important for us, so we will not dwell over this parameter too much. And at the end, there is response time given in milliseconds. This parameter tells us that it takes 30 milliseconds for LDR to establish its resistance after change in light level. So, we have to keep in mind that change in resistance is not immediate. This is important information, in case that we want to use LDR as some sort of counter, to count changes in light intensity. In the perfect scenario, we could observe and count 3 different changes in light level, from dark to light and back, in 1 second. To summarize, the most important thing for us is that, when there is some light, the resistance of our LDR is between 2 and 5 kiloohms, and when there is no light, the resistance is 100 kiloohms. Some additional notes. If you take a powerful light source, for example flash from smartphone, or expose LDR to direct sunlight, the resistance of LDR can go down to couple of hundred of ohms. Next, LDR is most sensitive to 540 nanometers light wavelength. This is green light. So, if you want to influence LDR with specific wavelength of light, green is the color to go. Working temperature of LDR is between -30 and +70 Celsius. Maximum operating voltage is 150 volts, and power dissipation is 90 milliwatts. Let's bring back our circuit, and LDR parameters for resistance under light and dark circumstances, and do some math. We will be using standard formula for calculating base current. So, when there is light of 10 lux, or more, resistance of LDR is between 2 and 5 kiloohms. In that scenario the base current goes from 1.15 down to 0.46 milliamperes, respectively. In special scenario, when light is of high intensity, base current goes high as few dozens of milliamperes. In dark mode of work, for LDR's resistance of 100 kiloohms or more, the base current is in range of few dozens of microamperes. From previous videos, we know that HFE parameter for 3 volts of VCE is around 179 to 194, depending of type of measurement taken. For simplicity of calculation, we will round up HFE to 200. Also have in mind, that for this particular type of transistor, maximum sustained collector current is 150 milliamperes. Let's do the analysis. So, when VCE is 3 volts, HFE is approximately 200, and maximum allowed collector current for NPN 2N3904 transistor is 150 milliamperes. We know all this from datasheet and previous videos dealing with HFE parameter. Also, let's remind ourselves that collector current is base current times HFE. The following table summarizes different values for base and collector currents, depending on values for LDR's resistance. Not good, right? So, when LDR is in well-lit environment, collector current exceeds recommended 150 milliamperes, and some. In special scenario, when LDR's resistance is very low, both base and collector currents are way above safe limits. So, in both scenarios, when LDR's resistance is equal or less than 2000 ohms, transistor blows, whether collector current being too high, or base current being too high, or both of them being too high. In next two cases, when LDR is lit, or in dark, both base and collector current are within safe limits, but this is also a problem. In both modes of work, light or dark, LDR provides enough base current to drive transistor out of cutoff mode of work. So, our transistor is always active, no matter if LDR is in light or dark. It never goes off in cutoff mode of work, so switch is always on. This is pointless. Clearly, we cannot use LDR as base current limiting resistor. If you have watched our previous videos, you know that beside base current, there is also one more condition that needs to be met, in order to properly bias the transistor. That condition is that VBE, the voltage between base and emitter junction, has to be at least 0.7 volts or higher. But this also doesn't help us, unless we use LDR and common resistor, to make a voltage divider. By definition, voltage divider is a circuit with two or more resistors in series, sharing same current. Since the current is shared, by using Ohm's law, we can calculate desired voltages, or values for resistors, depending on our circuit design needs. Also, sum of voltage drops across the resistors has to be equal to VCC. So, if we were to replace resistor R2 with LDR, and calculate the necessary value for resistor R1, we could make voltage divider circuit for our base emitter junction, to manipulate necessary voltages and drive transistor into cutoff, or active mode of work. So, let's do that. So, this is our new schematics. Now, resistors R1 and LDR, which we marked as R2, create voltage divider circuit. Our job is to calculate value of resistor R1, so that when LDR is lit, voltage drop across R2 drops below 0.5 volts, and voltage drop across R1 equals 2.5 volts, so that together we have 3 volts in total across voltage divider circuit. Remember that both resistors R1 and R2 share the same current. These are our desired parameters. Voltage drop across LDR resistor is 0.5 volts, and that is the same voltage across base emitter junction. In order for transistor to be active, this voltage needs to be at least 0.65 up to 0.8 volts. So, when we force voltage drop across LDR resistor, and base emitter junction to be less or equal than 0.5 volts, our transistor is off. Let's put all the known variables on the screen. We know that VCE equals 3 volts. When lit, resistance of LDR is between 2 and 5 kiloohms, so we will take average, and say that R2 equals 3.5 kiloohms. We want voltage drop across R2 to be 0.5 volts, and across R1 to be 2.5 volts. We know from before that resistors R1 and R2 share the same current. So, let's calculate shared current for R1 and R2. Since we know values for R2 to be equal to 3.5 kiloohms, and voltage drop across R2 equals desired 0.5 volts, by using Ohm's law, we calculate that current through R2 equals 0.14 milliamperes. Now, it is simple matter of calculating resistance for resistor R1. We know that current running through R1 is same as current running through R2, and that is 0.14 milliamperes. We want voltage drop across R1 to be 2.5 volts, so when we plug in the numbers into equation, we get value of approximately 18 kiloohms, for resistor R1. Since this is not standard value for resistor, we can choose next best upper value, and that is 20 kiloohms. Now, we have values for all of the components in our circuit. Next, let's see what happens when LDR is in the dark. When LDR is in the dark, its value changes to 100 kiloohms, or higher. The value of our one resistor remains the same, 20 kiloohms. Now, here comes that famous phrase, so often heard in electronics. Since value of resistor R2 is at least 5 or more times higher than resistor R1, we can disregard resistor R2 entirely. What a wonderful loophole. Our schematic now looks like basic transistor circuit, with base current limiting resistor R1. Next, we can calculate base current, using well-known formula. We get value of 115 microamperes. That is enough base current to bias transistor and switch it on. Assuming HFE to be 200, we get collector current of 23 milliamperes. Let's assemble this schematic on the breadboard, using LDR, NPN transistor, and some DuPont wires. For load, we will use multimeter, so that we could monitor collector current when LDR is lit, and when is in the dark. So, our circuit looks something like this. In the top left corner, we have power source of 3 volts, red and black wires. Our LDR GL5506, and two 10 kiloohms resistors, that form voltage divider circuit, that is connected directly to base of NPN transistor. Next, emitter is connected to negative rail with black wire. And last, multimeter is connected between positive rail of power source and collector terminal. Everything is powered up, so, our multimeter displays 0 amperes of collector current, as it should be. As it would be impossible to record video in the dark, we made a small black cap, to cover LDR to simulate dark conditions. As you can see, when the cap is on, LDR goes into dark, and collector current jumps to approximately 20 milliamperes, which is well within the tolerance, and our circuit is on. When the cap is removed, LDR is lit, and collector current goes back to 0, so our circuit is off. So, the conclusion is that our circuit works as designed. If collector current of 20 milliamperes is too small to power your load, you can always opt for relay, or increase power source to 5 or more volts, to build up the desired collector current. Have in mind, that you will have to recalculate all the parameters of the circuit, when you change the power source. So, this was fun. We made a switch, that can be switched on or off, depending whether there is a light or not. Cool. Please, before you leave, show your appreciation by liking this video, sharing it, leaving a comment, and consider subscribing to the channel. Thank you, and see you next time. Bye.